Free energy, delta G. You can go ahead and find this equation on your pink sheet, but delta G is equal to negative N Fe. And you know what delta G is, Gibbs free energy. N is the number of moles of electrons changing hands. F is something called Faraday's constant. On your sheet, it's actually 96,500. That's what Faraday's constant is. And go ahead and make yourself a note. This number is often seen as 1 mole of electrons is equal to a Faraday. So if you ever see a Faraday is equal to 1 mole of electrons. And obviously, the electrode potential is what we just figured out. So we can figure out the Gibbs free energy, whether it's spontaneous or not, from this equation right here. So let's do an example. Here's our equation, slightly different from before. So I'm going to write the half reactions, and I'm going to write the half reactions. If you noticed, I've got this one right here. Iron is losing 2 electrons. I've actually flipped this one from the back of the green sheet. So if you notice, I've already flipped this one for you because I want it to make it look like it was up above. So now all we have to do is just add those 2 together. Once I figured out which one to flip, I add them together, and that's what I get. Then if I plug and chug into here, the number of moles of electrons is 2, and you can see that here, 2 moles of electrons. This is Faraday's constant, 96.5. And remember, it's coulombs, and it's coulombs per mole of electrons. And then the voltage is joules over coulombs. And what I want y'all to pay attention to here is look and see what cancels. We got moles of electrons, coulombs over moles of electrons, joules over coulomb. And what you can tell is coulombs goes away, moles goes away. The only thing you're left with is joules. So we can figure out the delta G for this is this many joules. So I'll give you 2 half reactions, and you guys have to tell me which one gets flipped. Well, it's galvanic, and if you go back to your notes and look, galvanic cells always have to have a positive electrode potential. We have to flip the iron one. If we flip the silver one, notice what happens. This becomes negative 80, and this is positive 77. If you add them together, you're going to get a negative answer. But we know that galvanic cells always have a positive electrode potential. So which one are you going to flip? Well, you're going to flip the iron one, of course. That's the only one that you can flip that you'll get a positive answer from. I can actually flip this one and throw them together. And lo and behold, there's my equation for that cell. Silver is actually gaining electrons. Iron is actually losing electrons. And it puts out all of 0.03 volts. So which way does the electrons flow? The electrons flow. The iron is losing the electrons. The silver is gaining the electrons. And remember, who is the anode? Anox. So the anode is where oxidation is happening. And where's the cathode? Down here, that's where reduction is happening. And we can go ahead and do that. Anode, anox, cathode, red cat. And so you can look and say, yeah, okay, that's where reduction is happening. That's where oxidation is happening. Now, if you'll go ahead and get these steps in your notebook, and I will refer to this in class, but basically, I just want y'all to be able to follow along. How do we go from grams to amps? How do we go from liters of product to time? There's a certain amount of stoichiometry. There's usually 2 problems on the whole AP exam. Just remember that current is the same thing as amps, and an amp is a coulomb per second. Remember the second part, that's very important. Plating is, oftentimes they'll say, how much time has to occur at this voltage and this many amps to deposit or to plate out 7 grams of silver? And really what they're saying is how, if you deposit metal on there using electrolysis, using electro techniques, you can actually coat anything in metal. And that's exactly what they do with car bumpers and lots of other things. We'll actually show you this thing here now. Just look at it in your notes, kind of get it down. Other than that, I'll try to explain it in class based on those steps that we had before. You got to go from grams to moles of electrons, and that's pretty easy. That's just regular stoichiometry. And then you go from moles of electrons using Faraday's constant. That's this thing right here. You can jump from moles of electrons to coulombs. And then this number right here is because the problem says 5 amps. And remember that an amp is a coulomb per second. So I can go from moles of electrons to coulombs to seconds, because that's what an amp is. And then I can change seconds to minutes. Now, it doesn't really say to change seconds to minutes. It's just what I chose to do, but you can see how it just works its way out stoichiometrically. The key here is Faraday's constant, and also remembering that an amp is a coulomb per second. And here's another one. If I do 10 amps, well, an amp is a coulomb per second. So if I do 30 minutes, I can change that to seconds. And for every second, I'm going to let out 10 coulombs. And then this is a Faraday's constant. You can see here that that connects coulombs to moles, and we can get how many moles of electrons are going to be. And then jumping from coulombs, copper to copper 2, that's 2 moles of electrons. So for every copper, we've got 2 electrons. We go from moles of electrons here to moles of copper, and then we just use the periodic table to go from moles of copper to grams of copper. And we'll practice this some more in class. That's the whole point. The Nernst equation just says, what if it's not standard conditions? What if it isn't 1 molar concentrations? What if it isn't the same temperature? Now what's the electrode potential going to be? Use this equation right here, and don't be afraid, it's on your pink sheet. But finally we can go back to K. Now you really thought we were done with K, but we're not. So you can find the equilibrium constant for anything using the same equation. You can find K is connected to E this way. This is just an offshoot of the Nernst equation. I guess I should say that. But if you use the Nernst equation and solve for things, then you can actually, sorry, wrong way, my bad. So you can actually, no, that's not it either. Hang on. Wow, good job. You can actually find K if you know the electrode potential.